Welcome to this lecture series in real analysis. In this lecture, we will look at a technique or a theorem which allows us to compute the upper and lower integrals. So let us recall all the definitions that we need. So our setting is that we have a bounded function and write m to denote the supremum of all the values that the function takes, and write little m to denote the infimum of all the values that the function takes. Since f is a bounded function, m and small m are both real numbers. A subdivision sigma of the interval a comma b was defined as a list of numbers, a finite list of numbers. By that I just mean n numbers or finitely many numbers arranged in an order, where a0 is the first one is the left hand point, and the last one is, the first one is the left hand point, and then these are increasing, and the last one is the right end point. A picture, let me just draw a picture that we usually draw when we want to think about subdivisions. So here you have the left hand point, then you have others, dot dot dot, right? So that's how we can think of a subdivision. Now to a subdivision we associate these numbers. So for I from 1 to n, if sigma is our subdivision, this thing, then for I from 1 to n, we write Li sigma to mean the length of the ith part, meaning ai minus 1. So this is nothing but, for instance, if I were equal to 2, then it is a2 minus a1, and that is the length of the second part. This is the first part, this is the second part, and so on. So that's what that is. And then we have norm of sigma. So this has a name, norm of sigma. And its definition is you take the greatest amongst all of these lengths. Right? So it is measuring how fine the subdivision is. If this is small, the subdivision is fine. If this is big, there is at least one coarse part in the subdivision. The upper sum of a function f, this is the upper sum. This is defined as summation. And then here we write the, I'll write what this number is, MIF times Li sigma. So what is this number MIF? Maybe this is not the best notation. I should write MIF and then a sigma there, because otherwise it's not meaningful. So it depends on sigma, of course. Now what is MIF? MIF of sigma is the supremum of all the values that the function takes in the ith part of the subdivision. Right? So we saw what this pictorially means. If I don't want to refer to a picture here. We looked at it in detail, so let me not get into or spend more time on it. So that's the upper sum. Similarly, we have the lower sum. This is defined as this this sum, where now what is little mi sigma, and this is the infimum of all the values that the function takes in the ith part. And then we have the upper integral, which is the infimum over all subdivisions of the upper sum corresponding to the subdivision. So this sigma is running over all subdivisions of the interval a comma b. Now there should be a notation here that sigma belongs to all the subdivisions of the interval, but it's okay, I think you understand. Similarly, we have the lower integral. Lower integral is the supremum over all subdivisions of the lower sum. Okay, and we noticed last time that this inequality holds, where recall little m is here and capital M is here. And then we have this notion of refinement. So we say tau refines sigma if, so every subdivision you can think of a set of points rather than a sequence. You can think of a subdivision as a set of points. Any finite subset of the interval with the property that it contains the left and the right end point naturally gives rise to a subdivision. So we can think of a subdivision as a set of points, as we commented in the previous lecture. So we say tau is finer than sigma if the subset corresponding to tau is a superset of the subset or the set that corresponds to sigma. Think of tau as a set, think of sigma as a set. If then sigma is contained in tau, you declare that tau is finer than sigma. And if sigma is coarser than tau, or tau is finer than sigma, then in the lower sum, this inequality is preserved, and in the upper sum it is flipped. So these things we saw. Okay. So now let's proceed. I mean, there might be other things that we need to know, but it's okay. Oops. What did I do? Yeah. So these are some problems for practice. And now let us get started. So what is the point of today's lecture? We want to find a way to be able to compute these things. How was this defined? This was the this was the infimum of all the upper sums where sigma is a subdivision. And there are infinitely many subdivisions. How are we supposed to find this infimum? So in this lecture we will see a theorem which will make our job very easy, or relatively easy. It's still hard work to compute these things for a concrete f, but in principle we can do it all the time, and it will confirm to our physics knowledge. In physics, the way we used to compute areas under the curve when we learn it the first time, we will prove a theorem to that effect. Now everything will be rigorous. There we had dx and dx square, and we would ignore the dx square and whatnot. There would always be a lingering suspicion at the back of our minds that what we are doing is not legitimate mathematically. We learn to ignore it, but we don't need to even deal with it anymore. Even though it is good for intuition, it's not rigorous mathematics. All right. So suppose we are given a bounded function, and we have a subdivision tau of the domain of f. Suppose we have a point C arbitrarily chosen in the interior of this interval. So here I would like to make open interval. And then we define rho. Rho is another subdivision which is obtained by inserting the point C in tau. So we have the subdivision tau, but we define a subdivision rho where you have all the points of tau, but you have this extra point. So that's a subdivision of the domain of f. Rho is a finer subdivision. It has an extra point. And suppose k is the supremum, what did I say? K is a bound on all the values of, or all the range of values that f can take. So you take the absolute value of f and take the supremum over all possible values coming from the domain. Suppose k is a bound. Since f is a bounded function, you can always find such a k. So then we want to claim that the upper sums they don't differ by too much. For tau or rho, we can control the difference between the upper sums in terms of this number k and in terms of how fine tau is, so in terms of the norm of tau. If your tau is like a very fine subdivision, then you incur a very small error because k has nothing to do with the subdivision tau. K is just dependent on the function f. So the finer you make tau, the better will be the difference, or the closer will be the two upper sums. Okay. So why is that? It's a very, very simple proof. I'm sure if you just try it, you will get it immediately. And I encourage trying almost every lemma that you see by yourself. That is the best way to learn, but still it might help sometimes to look at what I discuss, because you may discover a new method of doing things. Anyway, here I don't think there is much scope to be very, very creative. So let's prove it. So I have some function, just for the sake of understanding. This is the graph of the function f. I have drawn a continuous function, but it doesn't have to be. It's just a bounded function. We have our subdivision tau. The points a0, a1, all of these are points in tau as shown. And c is an extra point. When you throw it in, you get the subdivision rho. Okay. So here is the thing. Let us define two numbers. One is m prime. M prime will be defined as supremum over all the values of f that the function takes in this region. So in this region, the supremum of all the points or all the values that the function takes. So let me maybe indicate it in this picture. So the height of this point, because in this region, the supremum of the function is this value. So this height is m prime. And what is m double prime? M double prime is defined as the supremum of the values of the function in this part, c less than equal to x less than equal to ai. So that is this value. Okay. And now it is easily seen that what is the difference between the two upper sums? The summands that appear in this upper sum, they are all same when you are dealing with the parts of the subdivision which have nothing to do with the part where c lies. Right? So the two summands where this and that differ are, or I shouldn't say two summands, but so there is a summand here for tau which corresponds to the ith part, and then there are two summands for rho. One is for this part and one is for that part. So one summand for this and two summands for that, those are the only things which will make a difference. So we'll just write them here. So this is equal to mi f sigma times li sigma minus maybe I'll push it down, minus m prime c minus ai minus 1 plus m double prime ai minus c. Right? Just unravel the definitions. There is not much to explain here. When you are computing this upper sum, you will be having this area here for the ith part, because the supremum over all the values that the function takes in the ith part is this point. It's just unfortunate that it happens to be the same point as the part here. I mean, that's because I've chosen a function like that. It didn't have to be. So yeah, just unravel the definitions and you will agree that this equation is correct. And now this can be written as ai minus c plus c minus ai minus 1. So I've just written this thing as that. Okay, and now we can open this bracket. So we get this thing minus m double prime, this thing minus m prime with, so this is with a minus sign, m prime minus, or is it? This is MIF sigma minus m prime c minus AI. C minus AI minus 1. I think it's correct. And now we just use triangle inequality. We are interested in this difference. I mean, we didn't really need to take absolute values because since rho is a finer subdivision of the interval, this is necessarily non-negative, right? So we didn't need to put an absolute value, but I will put it. And this is less than equal to. Right? And this is at most 2k, that is at most 2k. This is I mean, if you just look at the definition of k, you will agree that this is at most 2k. This is the supremum, this is the supremum that the function takes in a sub-interval. Same for this guy. So this is at most k and that is at most k, but when you're taking the difference, you'll have to write, or you can write 2k as a bound for both of them. So 2k times ai minus c plus c minus ai minus 1, right? And so this is just Li sigma, and that is of course at most the norm of, so Li sigma is at most the norm of this, so we have our expression. Very simple proof. It's best to do it on your own rather than look at all these grisly symbols. Looks quite horrible, but okay. Now a simple corollary. So if we have a bounded function and tau is a subdivision of the domain, and rho is a subdivision obtained by inserting r points. In the previous lemma, we had inserted only one point. Here we are inserting r points. R is some number, some positive natural number. Again, k is this bound that we have on supremum of all the values that the absolute value of f takes. Then we can approximate, or we can say that the difference between the upper sums corresponding to the two subdivisions, tau and the subdivision rho is the finer version of tau in some sense, is at most twice of k into r times the norm of tau. So just this r comes, and to prove it, you can just use induction. Inductively, you can enter r points. You start with tau, you enter one of those r points, you get tau 1, you enter another point, you get tau 2, and at the end you will end up with rho. Every time you apply the previous bound, and you will get this inequality very easily. Okay. So now, this is a theorem due to Darboux. Fix a bounded function. Then, for all epsilon greater than 0, there is delta greater than 0 such that whenever you choose a subdivision tau whose norm is smaller than delta, the upper sum approximates the upper integral with an error of at most epsilon or less than epsilon. So here again, we do not really need to write an absolute value symbol here because this is necessarily greater than or equal to that part. This is the infimum over all subdivisions, infimum of the upper sums over all subdivisions, while this is just one particular upper sum over some subdivision. So it is saying that to find the upper integral or to approximate it with some tolerance, all you need to do is fix some subdivision whose norm is small. Which subdivision doesn't matter. You don't need to cleverly choose a subdivision. Any subdivision whose norm is small will do. If you can compute it for your favorite or particularly chosen subdivision whose norm is small, you are fine, you have approximated the upper integral. So that's very convenient. And this statement that we've written can be written in a suggestive manner, that as you vary over subdivisions whose norm sizes converge to 0, you converge to the upper integral. Of course, what does this limit even mean? We have seen limits of functions, but not limits of things which take subdivisions as inputs and so on. So this is just a suggestive statement. Don't take this very seriously, but it conveys the idea very well. Okay. So why is this theorem true? Very simple. The proof is very, very simple. Fix an epsilon greater than 0, we need to produce a delta. Okay. Once we have an epsilon, we can find a subdivision. Let's call this subdivision sigma. So let sigma be a subdivision of the domain such that the upper sum corresponding to sigma approximates the upper integral with an error of, let's say, epsilon by 2. Why epsilon by 2? You will see in the proof. I mean, we've seen such arguments infinitely many times now. And say sigma is having n points in n plus 1 points in it. A1 up to an is sigma. And we needed to produce a delta, and we will produce a delta in terms of this number n and also the number k here. So what is k? K we will define as, again, the supremum of all the absolute values of the function. So define k as the supremum of this. And now define delta. So here is the key point. We define it as epsilon by 4nk. Now, why such a delta? That will be revealed in the course of the proof. When you do the proof, you don't know if this is the kind of delta you will need. As you write down the proof, you will fit it in later. So this is a post hoc calculation that gives you. But anyway, so some small delta, just think of it as delta is some small number, and now we need to prove that this happens. Okay. So let tau be a subdivision. Let tau be an arbitrary subdivision of the domain such that the norm of tau is less than delta. We will show that the upper sum corresponding to tau approximates the upper integral of f with an error of epsilon at most. And here again, we don't need to put absolute values. Okay, but I will put it. I just like it when it is there. Otherwise, it seems like things will escape out. Okay. So the thing is, sigma or the upper sum corresponding to sigma is an approximation to the upper integral. Let us take a refined version of sigma, or maybe better to say it's a refined version of tau. So define rho be the subdivision obtained by inserting the points in sigma into tau. So rho is nothing but the common refinement of sigma and tau, is all that I'm saying. So clearly we have then, because rho is finer than sigma, in particular we have that it also approximates the upper integral at least as well as sigma. This we clearly have. Maybe I'll box it. Wonderful. Sigma is a subdivision with this property. Anything finer than sigma will only decrease this part, right? So we have this with us. And now, using our previous result, we also know that this is at most 2k n norm of tau, right? So yeah, and that implies, now if we use this and that together, we just add them, this will cancel off and we will get, so what is this? 2k n tau is nothing but epsilon by 2. That's why we chose, okay, so I'll write one more line. So this is less than 2k n delta, and that is less than epsilon by 2, because delta was chosen as this horrible quantity. This is the reason why delta was chosen as such. And now we add this inequality and that inequality to get this thing minus the upper integral is less than epsilon by 2. Less than epsilon. So these two epsilon by 2 add up to given epsilon. And yeah, so we have it. Whenever tau is a subdivision with this property, for this particular delta, this delta has nothing to do with, delta is a solid constant. This n we obtained out of, some approximation that there is at least one such sigma which has this feature that furnishes us with an n, and using that n and using a feature of the function f, we have defined our delta. So delta is a solid number. Whenever we choose a subdivision whose norm is at most delta, we have the correct thing that we wanted, that the corresponding upper sum approximates the upper integral with the tolerance of epsilon. This is exactly what we wanted. And now we have this corollary that fix a bounded function, and suppose sigma k is the subdivision where the length of each part is constant, is the same. So you divide your interval into equal parts. So for instance, sigma 4 is obtained when all these 4 parts have equal length. What will be the length of each part? It will be b minus a by 4. The total length is b minus a, 4 equal parts, meaning each part has length b minus a by 4. So sigma k is defined as when you divide the interval into k equal parts. So the length of each part will be b minus a by k. So k parts, and then we know that by the previous result, that if you increase k, you will be decreasing the norm. The norm will be going to 0. If k is going to infinity, the norm of sigma is going to 0. And therefore, the corresponding upper sums will approximate better and better and better the upper integral. So you will get the upper integral in the limit. And similarly for the lower sums, we did not comment on the lower sums, but all the previous thing that we said, mutatis mutandis goes through for lower sums and lower integrals. So now basically the point is that we can use the subdivisions of our choice as long as their norms go to 0. We are fine. You calculate the limits. These are now solid numbers. You don't need to deal with an infimum. You just need to deal with the limit. That's much more convenient. And let us see an example. So consider the identity function defined on the unit interval. This is 0, that is 1. And we have the identity map whose graph looks like that. What is this upper integral? Right? So choose some k. We will use our previous corollary. Choose some number k. And we make subdivision so that length of each part is k. So length of each part is 1 upon k. There are k parts, each part with equal length. The total length is 1, so each part will have length 1 upon k. So that's our subdivision. This is a0, this is a1. a1 is nothing but 1 upon k. a2 is 2 upon k, 3 upon k, and so on. So this much is each part has length 1 upon k. And now what is the upper sum? What is the upper sum corresponding to sigma k? this is, well, what is the definition? The definition is 1 up to k. K parts are there, and then you write this number and then the length of sigma k, or ith part of sigma k. This is, yeah. So this is equal to, notice, what is this value? This is the supremum that the function takes on the ith part. On the first part, the supremum that the function takes is 1 upon k. On the second part, 2 upon k, and so on. So on the ith part, it is I upon k. And length is, of course, 1 upon k. So this is nothing but 1 upon k, 1 upon k square, and sum of all the natural numbers from 1 up to k, which we know is k into k plus 1 by 2, which becomes half times 1 plus 1 by k. So that's the upper sum for the sigma k, and if we take k going to infinity, we get, this is half. So all that happened was, for this sigma k, the upper sum was this area, the area of these bars. This is how we used to learn things in physics, and now they are well explained. So this area, as you take finer and finer, or if you increase the value of k, this overestimate will come down to 0, whatever that means. So we have this upper integral, and if you calculate the lower integral, it will turn out to be the same value. Right? So here the upper integral and the lower integral match. Later we'll prove a theorem which will be much more general. Alright, what about this particular function where we have the square function? Right? So it is again having domain 0, 1, and we are squaring the thing. Can we calculate the upper integral? So same drill, let k be some positive integer, and sigma k is as above. So what is this guy? Yeah, so what is MIF sigma k? This is 1 upon k square. For the first part, it is 1 upon k, this is I upon k square, not 1 upon k. The value of the function is I upon k whole square. So what am I saying? In the first part, what is the supremum? It's 1 upon k square. Then the second part is the square of 2 upon k. Then the square of 3 upon k, and so on, because it's an increasing function. So the supremum is taken at the last point. So that's what it is. And Li sigma again is 1 upon k. And we get, this is 1 upon k cube, sum up to I square, sum up to k of this quantity I square, which again we know from hopefully from our high school. This is k into k plus 1 into 2k plus 1 divided by 6. And that is 1 upon 6. I think, yeah, I mean 1 upon 6 plus 1 plus 1 upon 6 times 1 plus something. God knows what. It's some 2 upon k, and then some things which die down when k goes to infinity. So there is something wrong here. It cannot be 1 upon 6. It should be 2 upon 6. And do we get 2 upon 6? Yeah, so there is a 2 here. It's actually 2. It's 2k cube. What is inside? So let me put the k cube outside for the moment. What is inside? We have 2k cube plus something which has the square of k. Something times k square plus something times k plus something times, or just some constant. And now if you push in k cube, you'll get a 2, and everything will die down in the limit as k goes to infinity. So your answer will be 1 upon 3. So let me not do the details. You calculate this limit. Just calculate this limit as k goes to infinity. You will see it is 1 by 3. Yeah. So with that, I want to end this lecture, I think. No, I don't. there is this another exercise that I want you to do. I've called it the splitting theorem. This does not have a name in literature. Fix any bounded function, fix a point C in the interior of the interval, meaning in the interior of the domain of the function. Then the upper integral of the function is, I have written two terms. Now what do they mean? So this first guy here, what do I mean by the first guy? I mean, first you consider this function, which is the restriction of the function to this part. Since f was a bounded function, this is also a bounded function, and then therefore you can ask for its upper integral. You can ask for the upper integral of this function. That's what that denotes. So what I'm saying is, just show that you can break up the upper integral into two parts, and similarly for the lower integral. Just use Darboux theorem, you'll get it. So this is an exercise, and now I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.